Do we have any impedance matching experts in the room? No hands, that's good. I can say anything I want. I'm going to go ahead and start. Looks like we have a full room and I'm out of jokes, so we'll get going. This is an overview of impedance matching. It's not a detailed cookbook thing. Detailed cookbook presentations are basically useless anyway because you've got about 45 minutes. You don't remember most of it unless they give you an article or a cookbook to take with you. There's not much you can do about it. So this is an overview of what impedance matching is, how it is done, why you want to do it, and common techniques. We'll talk about balance a little bit as well. So thus the 101. So if you're expecting a detailed procedure about how to design a Pi-L network for your brand new 10 kilowatt amplifier, I'm afraid you're going to be disappointed. Okay, let's talk about impedance, get some terms out there. Impedance is just the ratio of voltage to current, how hard you are pushing to how much action you get. And there are a lot of analogies to electrical impedance. For example, mechanical analogy, mechanical impedance, if you've got a rotating system, is the ratio of speed and torque. And if you look at the drive shaft coming out of your transmission going to your wheels, you look at how hard it's working and how fast it's spinning, and you get an idea of mechanical impedance. And so your vehicle transmission is really an impedance converter. It's an impedance matching device. Your engine wants to run at 2,000 to 3,000 RPM. That's the peak of its efficiency and its torque curve, and so you want to keep it running there. But your wheels can't run at that speed all the time. You've got first gear, second gear, third gear, fourth gear, and so basically you've got this thing with a lever or some things with some gears in the middle, and the gear train is just an impedance converter. So you think of your impedance converters in your shack, they're nothing more than an electrical equivalent of what you've got in your car and you use every time you go someplace. And that's what a gear train does. It changes speed and torque at one combination to speed and torque at another combination. And that's a change of mechanical impedance, and that's all that electrical impedance converter does. It changes one combination of voltage and current to another combination of voltage and current, with the power going through both of those systems, the mechanical one, the gear train, and the electrical one. The power in is the same as power out, less frictional or resistive losses. So basically, now you go home and you think about your antenna tuner as a thing that's just like your car gearbox. Now, if we could use levers on our antenna tuners, that'd be kind of cool, wouldn't it? You know, and make them make little noises and things, overheat, lose their oil. The idea is to maximize power transfer out of the source, which is either a transmitter or an engine, into the load, which is an antenna or your drive wheels. It's the same problem. And you can also use impedance matching to reduce feed line loss if you do the impedance matching at the other end of the feed line. So the idea is to keep the power from bouncing back and forth until it finally gives up and goes out through the antenna or is lost as heat in your feed line. So if you can put your electrical impedance converter out there at the end of the antenna, you can prevent all that bouncing back and forth, and all your power goes down, goes out into the load. So you want to reduce your feed line loss there. It doesn't actually change the feed line loss, it just prevents it from operating on the signal that you're trying to send through the feed line. And it also makes transmitters happy. Solid state amplifiers are always one RF cycle away from total and utter destruction. Okay? So the control system, you look at a tube amp, you've got the tube, and it's a complicated mechanical structure, and it's got some matching networks, and pretty much that's it. You can do terrible things to a tube amplifier, and as soon as it cools down, you can go right back at it. But with a solid state amplifier, you do bad things to it, and the devices are so fast that all of a sudden they're gone. That's why they call them FETs. That's the noise they make when they blow up. So you want to keep your transmitter happy, okay? And you keep your transmitter happy by keeping the impedance in the range where it wants. Transmitters shut down their output power because they do not want to see that high current or that high voltage that results from power being reflected back down the feed line. And that causes bad things to happen, and they happen really, really, really fast. If you look at the 250 watt amplifier module that's in the handbook, it's about 1/3 amplifier and 2/3 control circuits, and that's basically typical. The transmitter is working away, one cycle away from destruction. The control circuit is desperately trying to keep it from falling off the edge of the cliff. So you make your transmitter happy with impedance match as well. What are the consequences of not matching? If you have an elevated SWR in a feed line, it increases the loss that is occurred by the signal as it goes back and through the feed, back and forth in the feed line. It does not change the intrinsic loss of the feed line. It just subjects your signal to more loss as it travels back and forth in the feed line. And there are lots of charts and nomographs and formulas for taking the matched loss in the feed line, which is the loss that you get if it goes through once and only once, and the additional loss from SWR where it goes back and forth in smaller and smaller fractions, bounce back and forth. Elevated SWR raises peak voltage and current in the line, not only at the transmitter, but in the line as well. And so if you have very high SWR and you're pumping it full of power and power is going back and forth, that peak voltage gets higher and higher and higher, and sometimes you can arc over a small feed line, and that's a problem. It's like if you just keep pumping away on the swing set, eventually you can go over the top, and that's a bit bad. I think you turn yourself inside out is the legend, but you don't want very high peak voltage and current in your feed line because it causes losses and punch through. As we talked about, unhappy transmitters will dial back the power. You can also reduce your receive sensitivity if you have a significant mismatch between your receiver input impedance and the feed line, or the impedance at the end of the feed line, or between the antenna and the feed line. So you want to do impedance matching there. It also reduces your SWR bandwidth. If your SWR is high in the feed line, you have a narrower range over which your transmitter is happy, or between tuning episodes. So you want to do that. It does not. Not matching does not change RFI. It does not change noise pickup. That's a function of your antenna system. It doesn't change your antenna pattern, and it doesn't cause bad breath or embarrass your mother. But there are perfectly valid engineering reasons to do it. We'll take a little sidebar. I like to chase rabbits and go off on alternate topics, but here's a related topic. Why 50 ohms or 75 ohms in coaxial cable? Where did that come from? Who picked that? There are different optimum impedances. If you go through the serious mathematics that are behind loss in a feed line, and for coaxial cable, they're well known, but they're complicated. You get these curves. Tell me the loss at different impedances. Tell me the power handling capabilities. Show me what the capability of peak voltage are. And you find out that right around 30 ohms, you get an optimized ability to handle power. A 30 ohm feed line can handle a lot of power without overheating. Just because of the geometry of the concentric conductors and using material that has a loss in the dielectric, and copper doesn't have infinite conductivity, so there's some loss there as well. So you wind up finding that 30 ohms, more or less, is the optimum for power handling. So in certain boot-shaped countries in Europe, they would want a 30 ohm feed line. And then 70 ohms, if you go the other way, that optimizes loss. Okay, you get the lowest loss. That's why the cable TV industry uses 75 ohm feed line, because they're worried about loss. They want to get their signals out to the far end of the line with the highest signal power, and so they use 75 ohm cable. Well, you've got 30 ohms for power handling, and you've got 75 ohms for loss. Right around World War II, when plastics became available, and you wanted to make coaxial cable, and they made it out of pipes and other things, they looked at the standard tubing sizes, and they made a compromise between power handling and loss, and they said, well, we can make reasonable coaxial feed lines out of the materials that we have that has about 50 ohms, and so it's going to hit this sweet spot between power handling and loss. And so everything happened during World War II, and all this stuff got standardized and things got picked, and pretty much we are stuck with it today. So 50 ohms became the system standard for RF inputs and outputs and feed lines, and so nobody had any incentive to move away from that in any direction. There's no reason today why we shouldn't be using 25 ohm lines or 100 ohm lines or something like that. But coaxial systems, unbalanced systems, wound up standardizing at 50 ohms during World War II because of these concerns, and that's why we have 50 ohm and 75 ohm cable. Now, you know, you can win bar bets now. Okay, so how are you going to match? There's a couple ways to do it. You can do it with resistors. You can simply trade off dissipating some power and use resistive attenuators, T-pads, all that kind of thing. It's cheap, but it dissipates power. Or you can use reactances, which do not dissipate power. A pure reactance has no power loss whatsoever, just the resistive losses in the capacitor or the inductor. It's very efficient, but it's also frequency sensitive because reactance changes with frequency. Resistors do not. Some examples of resistive matching: you take a 50 ohm attenuator and you put it between a signal generator and the circuit that you're trying to test. You can isolate the generator from impedance variations of the signal that you're trying to test. That's a very common way of making the signal generator happy. You put a 50 ohm attenuator, 10, 20 dB in there, and no matter what you do on the other side of the attenuator, the generator still sees the frequency or the impedance that it wants to see, and so it remains calibrated. If you made attenuator pads for an audio system, that's the same thing. There's T, there's pi, there's balance, there's unbalanced. Parallel and series resistors can be used to swamp out impedance variations. How many people have used a TFTD antenna? It looks like a folded dipole. B&W makes them. They look like a big folded dipole, but they go around and they come back, and the wires are about a foot apart. And then there's this mystery thing up in the top. Well, what's in the mystery thing is a great big resistor, and so what it does is it keeps the impedance from varying wildly as any normal antenna would do over that wide bandwidth. And so what you're doing is trading off some power dissipation against SWR bandwidth. And the military and government can simply say, well, we need a certain amount of communications margin here. We've got this amount of loss, so we'll just buy a bigger transmitter. Hams can't do that. We're limited to 1,500 watts. But military will say, okay, we'll just run it at 5 kilowatts or 10 kilowatts, whatever. It's a swamping resistor that simply burns up some power, and it keeps the transmitter happy by maintaining the SWR within a range of about 2.5 to 1 to 1 to 1. And really long runs of old coax are excellent at matching. The longer you run a coax, if you ever put up an antenna and use a little pigtail for it, you use your MFJ and you dial it up and you say, oh, the SWR is really high. It's like 1.8 or 2 or 2.5 to 1. And then you go back in the shack at the end of 500 feet of RG58, and you look at it and you go, well, flat here. Yeah. What's happening is the loss in the line is basically flattening your SWR curve. And there are some curves in the handbook and the antenna book that will tell you if you have this much line loss and you see this SWR, here's what your SWR is out of the load. So you can make any antenna look really, really good just by using really, really bad coax, or really a lot of it. So that's another way to match. Here's another way to match. Transformers. Your basic transformer, what does it do? It takes power in, one combination of voltage and current, and it sends power out, minus a small handling charge, and another combination of voltage and current. It's an impedance matching device. All it does is transfer, even a power transformer takes power from your grid at 120 volts and 1 amp and changes it to 12 volts at 10 amps on the other side. Same amount of power, just a different ratio of voltage and current. And the appropriate equations, I realize that every time you use an equation, you lose half the audience, but you guys are probably with it. Here are your equations. Voltage out equals the turns ratio times voltage in, and current works the other way. Current out is equal to current in divided by the turns ratio. So the turns ratio, secondary to primary, is what governs the impedance ratio. You can see the analogy to mechanical systems. This might be number of teeth on the output gear, number of teeth on the input gear. The equations are almost the same. You can use broadband transformers. Audio and modulation transformers are very broadband transformers. They have to take audio signals from down around 100 hertz all the way up into, if you're doing music, which is of course illegal on the amateur bands, but if you're doing music like at an AM station, you're talking 10 to 15 kilohertz. That's a pretty wide bandwidth. That's a 10, 15 to 1 bandwidth. And that's a broadband transformer. The analogy would be at RF, which you went from 160 meters way up into VHF. Okay, so that's a long way to go. So audio and modulation transformers are broadband, and you can also get the ferrite and powdered iron core transformers that we're accustomed to here at in amateur radio. And it's the same thing. The number of turns on one side, number of turns on the other side. Think of them as teeth as a gear. They change one combination of voltage and current into another, and so that's what they're doing. It's impedance matching. It's according to the turns ratio squared, if you work back through the math. So the ratio of impedance between the secondary and the primary, and this is called the reflected repeat impedance. The impedance that you see if you look into the primary circuit is controlled by this turns ratio, n squared. So if n is 2, the ratio of impedances is 4. So if I put 100 ohms on the secondary, I have a turns ratio of 2. What I see at the primary is 100 divided by 4, or 25 ohms. If I have a turns ratio of 3, the ratio is 9, and so what I would see on the primary is 11 ohms. That's how it works. Here's an example of a broadband transformer. This is from the handbook. It's got a powdered iron core. It's one of the T200-2 or FT240-2 or what have you, HF cores, and it's got a bunch of different windings on it, and by controlling the relay here with these little control lines here, you can switch it between 1, 4, and 16 to 1. By changing the turns ratio and the way that these windings are connected. I'm going to take a little time out and talk about balance here. Excuse me. Balance it's abbreviation for balance to unbalanced. Where balanced means that both of the conductors on the balanced side, either the feed line or the load, are symmetric with respect to ground. Okay? They're open wire line, free space dipoles, any load or system that has both terminals symmetric with respect to ground, whatever your ground reference is, whether it's a big sheet of copper in your shack or the earth itself, that's a balanced system. An unbalanced system is the conductors are asymmetric. That's all it means. You can have coaxial cable, single wire feed lines, or systems that have an enclosure return, so you bring the cable back in and one side of it, even if it's twisted pair, one side connects to the outside of that metal enclosure, which is then connected to ground or something. That's an unbalanced system. Ground plane verticals are an unbalanced system. So the dipole, symmetrical dipole in free space, and we all know, we all put up our antennas in free space, that's a balanced system. Unbalanced system would be a ground plane or a dipole that's not in free space. Like one of it goes over the roof of the barn that happens to be a metal roof. Okay, that's a very unbalanced system. Okay, an un-un is a transformer between two unbalanced systems. Instead of having balanced to unbalanced, you have unbalanced to unbalanced. Current balun, there are two types of balun. Current balun forces equal currents into the load terminal. By whatever mechanism it's got, it makes sure that when the power goes through it, equal current flow in each terminal of the load. A voltage balun makes sure that it has equal voltage at each terminal of the load. So they're two fundamentally different things, and you have to look at the application and the type of balun if you're going to get the desired results. A balun is a function. It's not a device. There are a lot of devices that perform this function, but a balun is a function. Any device, any at all, that transfers power between balanced and unbalanced systems, isolates the balanced and the unbalanced system, transfers power between them, is a balun. That's what it is. You can have different types of transmission line baluns where you wind them around cores or you connect them up in different configurations. The resonant transmission line sleeve baluns where you have the half wavelength extra piece that goes over to the other side. You can have the Q3Q balun that I wrote about in QST. There's a bunch of different ones of those. You can have ferrite bead on the outside of a coax that blocks current from flowing on the outside of the coax shield. You can simply coil your coax up into a coil and make the outside of the shield into an inductor, which has some reactance, which blocks the current. All of those things are baluns. Doesn't matter whether the guy down at the store calls it a balun or not. If it's a device that takes power from one type of system and transfers it to another type of system while isolating the two, that's a balun. An impedance transformer is not necessarily a balun, and a balun is not necessarily an impedance transformer. Okay, you can mix and match those things. Sometimes you go out and you buy a 4-to-1 current balun. First of all, there ain't really no such thing in one device, but you can buy two devices in a package where you have a current balun followed by a 4-to-1 impedance transformer, and you put it in a tube in a package and call it a 4-to-1 balun, a 4-to-1 current balun. Nobody knows the difference. But an impedance transformer is a different animal than a balun. All that a balun is doing is trying to isolate two systems and force equal voltage or equal current onto the terminals of the load. I feel better now, thank you. This is my standard rant these days. One thing that I want to point out though, if you use a voltage balun at the end of the transmission line and you're trying to make sure that an antenna has equal currents in each side, okay, unless your dipole is in free space, okay, it's probably unbalanced. And so if you just put equal voltages on each terminal and you don't have equal impedances on each side of the antenna, you will not get equal current. If you don't get equal current, you don't get equal radiation from each half of your dipole, so you don't get what you think you're getting. So what you need to do in that case is to force equal current into each load of the driven element or the antenna, and that's what makes an antenna radiate. Current. In making electrons go back and forth in a straight line. That's what causes radiation. So if you can cause that to happen equally on each side of your load, then you'll have a balanced system. But if you just put equal voltages out there, they'll take whatever type of impedance they've got, and that's what current you'll get. So a current balun is better at an antenna for impedance matching and power flow isolation than a voltage balun. Okay, let's go back to reactive matching. All that reactive matching means is using L's and C's. Engineers love fancy words, okay? So we won't say using L's and C's. Oh no, people could actually understand that. We'll say reactive. So when you talk about reactive impedance matching, all it means is circuits made out of inductors and capacitors. And network is just a fancy name for circuit. So when we say reactive network, what we mean is a circuit made out of inductors and capacitors. A very common example is an L network, where the circuit components are arranged in such a way that when drawn in a schematic it looks like an L. There's two of them. You can have pi and pi L networks. The pi looks like a Greek letter pi. You have two components going ground on the sides and one in the middle. So it kind of looks like a pi. Pi L, you add one more component in series, so it kind of looks like a pi network with an L network tacked onto the end of it. T networks look like a T, surprisingly enough, where you have two series components and one shunt or parallel component in the middle. Another way to do it, tap coil LC tank circuit. If you've ever built a half-wave vertical, bobtail beam, that sort of thing, you're trying to apply power to an antenna at a very high feed point impedance. Remember, feed point impedance is just the ratio of voltage and current at that point on the antenna. One of the common ways to do it is to make a resonant circuit with a parallel L and C and set it up to be resonant, and then you move your feed point along that coil until you find the 50 ohm point. At the top of that coil, you got the very high impedance, maybe a couple of thousand ohms. At the bottom of the coil, it's connected to ground, 0 ohms. Somewhere in between a couple of thousand and 0 is 50. And so you just move your tap point up that coil until you get to 50. There's no mystery to it. You're just kind of fooling around and moving the tap point until you get what you want and make the transmitter happy. Networks can be high pass, meaning as you increase frequency, they pass more of the signal, so they act like a high pass filter, or they can be low pass. And the way to tell is you look at the series components. What are in series in the line of your signal? If you see mostly capacitors, then it's a high pass network. If you see mostly inductors, it's a low pass network. And that's basically the way you tell. But reactive matching, as you all know, if you've got an antenna tuner, it only works at one frequency. Okay? All these reactances change. X sub L equals 2 pi LF. X sub C equals 1 over 2 pi FC. Those change. As you change F, the reactances change. And the reactances change, it's like having gears that change the number of teeth as you change the speed of the system. Well, that won't do, okay? So you have to readjust it. But they only work at one frequency. Resistors work at all frequencies. The reactances work at just one frequency. Here are some diagrams. This is not a lesson in Eastern philosophy. I was really amazed to see in my college days that the Smith chart had yin-yangs all over. It's really kind of interesting. If you went to any of the presentations yesterday, like Mr. Harriman's Smith chart presentation and Jim Brown, you saw the Smith chart. This is the outside of the Smith chart. Here's that center point where impedance is normalized to the characteristic impedance of the feed line, and Jim showed you can move around. Okay, it's what I call knight moves on the Smith chart. It's like in chess, where you can move a knight. You have to move in 2 squares in one direction and then 1 square over. Even if you want to get right just to that next square, you can't do it with the knight. Okay, you have to move up and over, and that makes the game exciting. What also makes impedance matching exciting, because when you have a reactive network, an L network which has these 2 components, and you can see 8 different configurations of L networks, you can only make knight moves on the Smith chart. You can move along constant admittance circles, or you can move along constant impedance circles. That's it. You're adding a little admittance, or you're adding a little impedance. And so you're just moving around on this distorted street map of the impedance world. And so L networks, all these different configurations here have different areas on the Smith chart that they can match. For example, this white area up here shows all the possible impedances that this configuration of an L network can match. If you have the right relationship between what you've got and what you want, you can use this particular configuration. But if you don't, you can't get there from here. Okay, it's one of those deals. So you basically, what you do is you take this one and you turn it around and make this one, and you can see that the allowable matching areas are down here. So now I could not take this point, if it was down here with this network, and cause it to get to here, which is where SWR is 1-1. Can't do it. So what I would have to do is turn that circuit around, and now I can move around and get to 50 ohms. So depending on the relationship between the input and the output impedance, you have to choose the configuration of this 2-component network here, and that's how you match. Okay, it's like if you want to go from really high speed really low torque to really low speed, really high torque, you've got to have the big gear on the right side of the gear train, okay? Otherwise, it ain't going to work. So what do? You turn your gear train around, then it works, okay? So basically, it's the same thing with L networks. These guys down here are a lot less common in amateur radio. These are the ones you will see in impedance matching for feed lines. These are the common ones. These guys you'll see in amplifier outputs and other types of circuits like that. This is from the Microwave Experimenter's Manual, and it's in the handbook now. It has the two components. As I said, if it doesn't work, turn it around. If you go back and you look at these guys, this one, this one, this one, and this one, they have the capacitor in series. Okay, that's a high-pass network. This one, and this one, and that one that has the inductor in series. That's a low-pass form of the network. So if you're worried about harmonics and that sort of stuff, you need to make sure you choose the right kind of network. Here's your pi network. You can think of it as two L networks back to back. I took my big circuit cleaving knife and I cut right through here. What I would see is an L network. I've got an L network here, and I've got an L network here. And I've just connected them back to back. So it's like having two gear trains connected together. Now why would you want to do that? Well, because it allows more gradual impedance change, and it transfers power in two steps. It's like putting an idler gear in the middle of your gear train so that you don't do all of the transformation in one really big change between really big gear, really little gear. That often doesn't work, and you'll see gear trains have 2 or 3 sets of gears that gradually transform speed and torque at one combination into the other. It's the same kind of thing here. This has better bandwidth, and it can handle larger impedance ratios. That's why you'll see this in a tube amplifier where this plate impedance is several hundred ohms to several thousand ohms, and the output impedance is 50 ohms. So this is a better solution for that than trying to do it all with one L network. You could do it with one L network, but it would be very touchy, very sensitive. So you get better results by using a pi network. If you add the output inductor, if you took this inductor and added it out here, you would get additional harmonic suppression, and that's also used in some kinds of amplifiers. Here's a T network. This is typical of most antenna tuners today. If you go down there and you open all the boxes before the HRO guys could pull you away from the antenna tuner display, you would see this kind of a circuit. You would have a variable inductor in the middle, either with a nice little turns counter and a little slidey wheel inside, or a switch where you could switch this tap, ding, 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 up along the inductor. And then you have a pair of adjustable capacitors, one labeled antenna, one labeled input or transmitter, that sort of thing. It's a high-pass network. This was not popular in the early days because it did suppress harmonics. And when we were building our own transmitters, well, they tended to have harmonics, and we worried about this. This is not so much of a problem today, so that's not so much of a design constraint. But it's usually built this way now because this is easier to build. It's easier to build, and it's cheaper to make 2 adjustable capacitors in series and 1 inductor to ground. You could do exactly the same thing with inductors and capacitors, but then you'd have to have 2 adjustable inductors, and that's more expensive than solving the problem with a couple of capacitors. So that's typically why you see T networks now. If you like T networks and you want to have some fun and you're bored, okay, you go to W9C Up. Just Google W9C Up T network. You don't have to know anything anymore. We don't have to know anything, you know. You just get on Google. That's why I got a smartphone. I got tired of forgetting what it was that I was going to Google when I got home. Okay, so I wanted to do it right on the spot. And the first thing, you'll never guess. Called Helen up. I said, "Honey, I got the smartphone." She says, "It got Google on it?" I said, "Yeah." I said, "What do you want to know?" And she says, "Just a minute." She says, "What's the favorite food of a capybara?" I go, what? What's the favorite food of a capybara? I said, well, I'll call you right back. So, hang on. Corn on the cob. Okay, so I call her back. So now you all know what the favorite food of a capybara is. Okay, so we don't have to know anything. Just Google W9C Up and tuner, and you will get this cool Java applet which will appear on your computer screen. And what you do is you tell him what your load impedance is and how much reactance and what frequency you're at. And you can also modify setup, but it assumes you're talking about a 50 ohm system. And suddenly you've got numbers. It says the SWR is this and the percent loss in the tuner is this, and it changes it into dB. And you click on it with the mouse and you can turn these little wheels and you can watch the meter go back and forth. It's really, really cool. And you can also make it go auto-tune and go, it's pretty neat. It's just a simulation of that T-network, and it's fun to work with. What's really important is not that it works, but it tells you how much loss is in your network. And sometimes T-networks are famous for being able to tune up into themselves. They have a very, very wide tuning range, and so just the stray capacitance at the output and a little loss in the feed line and the connectors and stuff is enough impedance that these things, you can get them to match up into themselves. The currents and the voltages get really high, so if you've got your amplifier going, you may smell something. You'll find the weak spots in your system real quick, but if you do that on a simulation, we haven't been able to simulate the smell of a burning component yet, but you'll see right now this says 41.4% loss. That's a lot. You're losing 2.3 dB through the tuner in this configuration. And this is covered in W9CZR's book on antenna tuners. Yes, sir?
Yeah, does that somehow include some assumed losses resistive, or?
Yes. Does it include some resistive losses and stuff? If you go into the setup, you can change things around. W9C Up's done a lot of this kind of stuff, really cool stuff. This guy works at Fermilab, and he's one of these guys that does more in a week than the rest of us get done in our entire adult life. So, transmission line transformers are also very, very cool. How am I doing on time here? I need somebody in the back to wave a high caliber weapon when I get close to running out of time. Synchronous transformers, I did a column on these things. How many people have coated glasses to reduce glare? You pay that extra fee? Okay, you're using a synchronous transformer. What a coating is essentially some modified version of one or more coatings of material on the front of a lens that has the right characteristic optical impedance to act as a reflection beater. Okay, and it does exactly the same thing as a quarter wave section in a transmission line. It sets up a series of reflections that cancel reflections back toward the source. Quarter waves are the most well-known. It's called a Q section in some literature. A quarter wave transformer that is 1/4 of a wavelength long will take this impedance, Z2, and turn it into Z1 if it has this characteristic impedance, the geometric mean between the two. So if I have 100 ohm output impedance, like say a loop, a quad loop or something like that, and I have a 50 ohm feed line, then I go find some coax with a characteristic impedance of 50 times 100, 5,000 square root 70.7, and 75 ohm coax will do just fine for that. And I cut a quarter wavelength section, and by golly, 100 ohms over here turns into 50 ohms over here. And it sets up a series of reflections in that line that when finally you sum them all up here, it acts like there are no reflections. The reflections are all phased and amplituded just right. Is amplitude a verb? Verbing weirds language. So it just sets it up. So Z1 thinks it's perfectly fine out there. Okay. You can also use that surplus hardline that you got that's been sitting around in your garage, 75 ohm hardline, and you're thinking, I can really use that, but it gives me an SWR 1.5 to 1. We use these little 12 wavelength transformers. This is covered in the handbook, in the antenna book, and I wrote a column about it. You can find it online. This is really, really common. Again, it's a single frequency match. That's where the word synchronous comes from. It is Its properties are determined by the timing, the phase of the reflections that it sets up in the transmission line. It's almost like putting a weight on the wheel of your car. It doesn't change the fact that the tire is out of balance. Okay, your tire is still out of balance. But what it sets up is an alternative set of wobbles that when they're summed together in the axle, which is here, the amplitude of the wobbles and the phase of the wobbles is such that they cancel out. Okay, so your axle and the rest of your car is perfectly happy, even though your tire is out of balance and you put a weight on the wheel, so the wheel's out of balance as well. The two out of balances balance out, and that's how it works. Antenna feed point matching. Okay, we also do some cool feed point matching up at the antenna. This is where you want to do impedance matching if you can. If you can make the antenna look like 50 ohms, you can hook a 50 ohm cable up to it, all the power goes through it once and only once, there's no additional loss from it bouncing back and forth. The voltages don't get high, the currents don't get high, and everybody's happy. So there are both structures, different kinds of mechanical stuff up there, and there's also transmission line techniques. They mount right at the antenna, or sometimes they're part of the antenna feed point assembly. They do require adjustment at the antenna. You got to do it while you're hanging on, or you got to lower the antenna and mess with it, and pull it back up 800 different times. They have to be adjusted at the antenna, although there are some techniques now. For example, I made a little vertical and I put one of those auto tuners out at the base of the vertical, and so I just say tune, and I've got my little tuner right out at the vertical, so I can use RG8X out to this thing, and it's not too bad. Whereas if I put the tuner in the shack, I'd still have high SWR in the RG8X, and on some bands I'd have a lot of loss. So putting it at the antenna is a good thing. But again, it's one band match. Here's the original. If you go back to the old antenna books, this is a good reason to look in the boxes and the club tables at Hamfest, because sometimes you find things like the 1939 antenna book for $4. Ka-ching. It's great. So here's this picture. You got a half wavelength dipole. Well, right in the middle, the impedance is something like 70, 80, 90 ohms, something like that. And out at the ends, it's a zillion ohms, okay, theoretically infinite, but more like 3,000, 4,000, 5,000 ohms. And in the day, 600 ohm line was really popular. Well, somewhere in between 50, 60, 70, 80, 90 ohms and a gazillion is 600. So somebody just got the bright idea, so look, we'll just move the connections farther and farther and farther apart until we get to the 600 ohm point. And so what happens is your open wire line came up and split, and you've got this kind of triangular thing, and that's why they called it a delta match. It looks sort of like a Greek letter delta. And as we all know, if we name something after a Greek letter, that gives it like 10 dB of extra goodness. Okay? So basically, you're just finding the right impedance, okay? And that was the first thing that they did. And typically, they came up with a set of guidelines for this. If the distance between the 2 points is 0.12 wavelength, and the peak of the triangle is about 0.15 wavelength long, that was a pretty good match to 600 ohm line, assuming certain things about this antenna, that it was a half wavelength long, certain frequencies, a certain electrical height above a certain electrical type of ground. And that worked well enough that it became known as the delta match, and that's originally the first kind of antenna matching structure at the antenna. Well, they moved on and said, okay, again, we want to do this balanced line thing. We want to try this a different way. And they made it into a T. They basically took that triangle and they flattened it out. And this worked better for low impedances. And they found this is like a folded dipole where you can take an impedance and multiply it up to make a better match to an open wire line. And again, they found a combination of A and B that worked. And it sort of looks like a T where the line comes up and it goes this way. Another way of doing this is instead of moving the connection points back and forth, which is pretty inconvenient. You have to take the antenna down, you have to move things, solder stuff. They said we can do exactly the same thing by putting a couple of series capacitors in here, and I just adjust the both of them until I get a match in the line. So this is called the T-match. It's a balanced transmission line and a balanced load, which is great for dipoles and antennas that are built with isolated driven elements. Okay, so here's the gamma match. What the gamma match is half of the T-match. If you go back to the T-match and you just make half of it go away, what you get is the gamma match. That's what it looks like. And again, it's kind of a folded dipole thing where you're taking a low impedance and transforming up to a high impedance. This looks like a little piece of shorted transmission line. Dave Leeson has written some really good papers on this. The variable C, sometimes you do see an actual variable capacitor. It's a little refrigerator box or something up there. What's more common though is a tube, a hollow aluminum tube, and a big long piece of coax center conductor surrounded by a dielectric. So you get a tubular capacitor that goes in there, and you move that piece of wire in and out, and that varies your C right here, and then you move the shunt back and forth in the output until you get the impedance that you want. This is really a very good improvement because spiders can get in there and build nests, and then they arc over when you run power right at the beginning of the contest, even though it's been perfect all week long. Okay? So that's definitely improvement. But this is a good thing because note that you can connect the shield of the feed line right to that electrically neutral point right in the middle of the antenna. So this became real popular when people started building all metal antennas. The term used to be plumber's delight because everything was made out of metal. Before that you had a wooden boom, and you see old drawings with little beehive ceramic insulators holding the metal elements and all that kind of stuff. And then people said, hey, aluminum tubing is getting cheap here. We can use all these aluminum fittings and hardware. And back in the late 50s and early 60s, plumber's delight really caught on. Everything's at DC ground. It's a lot easier to deal with. You don't have to insulate your driven elements. So the gamma match became a big deal. It only works at one frequency. Okay, it only works on a monoband beam, so you can't use it on a tribander. Here's the beta match, also called a hairpin. What that is a coil that's attached across the feed point. And this is like an L network. You adjust this driven element so its impedance is a little bit capacitive. That's the capacitor of the L network. And then you add the inductor across it. So you have an inductor at the input, you have a series capacitor that is part of the driven element impedance, and that forms a little L network to take the low impedance of this beam element and transform it to coaxial cable. Now, there's also a one-to-one Balan involved because this is an unbalanced system. This is a balanced system. If you're going to use a hairpin match, your driven element has to be insulated from the ground of the boom and the tower and everything else. So I think High Gain was the biggest proponent. Telrex also made monobanders, and they had a sleeve around the driven element where you would attach pigtails for your coax, and then they would have a long wire that would go down the boom, and this is an electrically neutral point, so I can actually take a sheet metal screw and hold that to the boom at that point, and then bring the other side of it back. And so I have this inductor across it, but it's actually mechanically pretty sturdy because I'm holding one end of it down. So this is sometimes called a hairpin match because this is a long folded piece of wire. How many people have ever built a tape measure beam for direction finding or something? Okay, a few hands going up. And they have you put this little hairpin across the driven element. That's what this is. Now, I saw a hand go up over here.
No, one's response.
Okay, all right. And anyway, it's just like an L network. It uses the C in the antenna's driven element impedance as part of the network. Here's some references and tools for you. I'm kind of attached to these two books. I don't know why. The antenna book software, TLW, YW, Match, all this kind of stuff. We've got a new version of Gamma coming out that doesn't blow up for certain oddball combinations of numbers. This is good stuff. This is the accumulated knowledge of amateur radio for the last zillion years, and it's good to have these things around. You know, just you either have one every few years or what have you, or your buddies buy one and share it, whatever. The software is really good. Most people, I'm amazed that people don't open up that little CD at the back of the book. And you say, well, it's on the CD. And they go, what? Well, there's a CD-ROM in the back, and it's got like 800 articles and some free software. No kidding. Yeah, it really does. So open it up.
It's a PDF.
What's that?
And just a PDF.
And PDF. I put all my stuff on my Kindle. So I've got my entire reference library, you know, all these old antenna books that are on PDF, and my handbook, my antenna book, and all this stuff. They're all on my Kindle. I can just drop them in my briefcase. Yeah.
And how do you read on the Kindle? That PDF doesn't have the ability to adjust the font, not like the Mobi, which I'm not quite. You understand that? How do you?
I just deal with it. I just deal with it. You know, some of the stuff isn't a font big enough to read. I mean, I know what I'm looking for, so you know I can find it. This is a new book by W9C Up. It's been out about a year now. Guide to Antenna Tuners. Joel has a lot of good stuff in there, a lot of circuits, a lot of explanation, why these things work, why they don't work. The ARRL online archives of QST are really cool. Go look for George Grammer's stuff. His name is lost. He's one of these guys that you never hear of anymore. W1 Delta Foxtrot. And his articles were fabulous. What I would really like to do is bring all of his tutorials out of QST and make a book out of them, even just a PDF, because they're so good. A series on antenna matching, a series on impedance matching networks, all sorts of stuff. I mean, as Jim said yesterday, the ancients have stolen all of our inventions. Well, it's true. If you go back and you get a copy of Terman or Laporte or any of these guys back from the 30s, you'll see almost all the stuff that we use today. Of course, it's an open wire line. Mostly and not coax, but all that stuff is already there. It's been done 70, 80 years ago. We just keep forgetting it and rediscovering it. Okay?
What's George's last name?
Terman, T-E-R-M-A-N. He's a professor at Stanford. What? Oh, Grammer. G-R-A-M-M-A-R, I think. Whiskey 1 Delta Foxtrot. If you go back and search the archives for Grammer and then go back to his first articles toward the end of his career, he was did a lot of product reviews and stuff. The antenna compendiums are really good, just for browsing through. You know, they may have a solution for what you're looking at. Everybody's antenna situation is different. Where you install it, what type you want, how high it's going to be, what your ground is like, all this kind of stuff. So your goal should be to continually fill your brain full of knowledge. And just by reading these compendiums and these books, you'll put a lot of that knowledge in there so that when you back up, like Ward's presentation on building his antenna, you've got this huge problem space to deal with. How do you whittle that down and make a choice about what kind of an antenna you want and what kind of an impedance matching network you want and all that stuff? You need to have all this information available to you so you can go and start chopping away at that big problem. And this guy writes this column in QST that comes out every month, and it's kind of cool. I'm sort of partial to it. We just finished the next 60 experiments, so there'll be another compendium that comes out after the first of the year. Additional goodies. Transmission Line Transformer by Jerry Sevick. Sadly, a silent key, but did a lot of work for RCA and classic books. There's 2 or 3 floating around by Sevick. I think this is the one that's still in print. Any volume of reflections that you can get your hands on. This was a groundbreaking, eye-opening, mind-blowing, myth-busting series of articles in the 70s in QST. Walt finally got tired of reading all the baloney, or malarkey as we currently call it, in the articles about SWR and stuff like that, and wrote this series of 7 or 8 articles. And it just turned everybody's head right around. So this became a book, very good book. It was sold by World Radio Books, and I don't know whether somebody else is still making them available or not, but I know some of them are still out there.
CQ had it.
Okay, good. LB Sevick, W4RNL, regrettably another silent key. Go to his website. He wrote a lot of stuff for QST, and his website has thousands literally thousands of articles on antennas and transmission lines and antenna modeling, and the guy was just a volcano of information. It's free, you have to sign up and give him a password, and then you'll get ads from Antennex, but you know, that's why God made the delete key if you don't want to do that. And so Sebek's stuff is really good. He also wrote some antenna modeling courses for the league. Online calculators, there's tons of them. Go to Microwave Kitchen, Microwave 101, RF Cafe. If you just Google impedance matching calculator, again, you don't have to actually know anything, just Google it. You'll get links to hundreds of different sites with lots of calculators. The best known calculator package is HamCalc by VE3 ERP. He was having trouble compiling it to run on Windows 7 systems, but the package is still out there. I believe it's free. Had 150 something different ham radio type calculators, useful little things that would run in a DOS window. And so this is another little thing for your toolbox. These textbooks are all available online. They're out of print, so you can get them as PDFs, or you can find them as reprints. Radio Engineering by Terman. Any one of those versions is good. I think the last version was published in 1953 or 4. I have a 1943 copy. You know that cool chart in the front of the handbook that's been there since time began that has the big X's with all the reactances and frequencies and all that kind of stuff? That's from Terman. Okay, so a lot of that stuff came out of this guy's basic Bible of radio engineering. Radio Antenna Engineering by Report. This is another one. Now you're starting to get into the professional literature, but if you really want to find out, you can get this, and it's online. It's a PDF that's for free. And the Antenna Fundamentals chapter of the ARRL antenna book is real good. It just summarizes all of the basic terms and basic know-how and packages it into one thing. I went through the whole book and I started pulling out these little pieces of introductory material and crammed them all into the Antenna Fundamentals section. So if you just want to read that one, that's a good place to start as well. Thanks for your attention. I'm open for questions, comments, and $20 bills. Okay.